Welcome. So we're going to graph these two, the stretches for the cube root, for the square root, and then the cube root. And I'm going to create a table of values so that you can discover what that number under the radical, that coefficient under the radical in front of x, what that is going to do to our function. Right? And so I have y equals the square root of x already graphed. This is in your notes, so just follow along. All right, so we're going to create a table of values. All right, so the first one we're going to do is y equals 1/5 x. So we'll plug in for x. And there's most of my x, half an x. There we go. Okay, and we'll get an answer for y. And we plug in for x. All right, so I want to choose numbers that will be friendly to graph. Right? So I'm not going to graph every possible point that would fit on my coordinate plane here. I'm going to choose wisely, right, so that I get friendly numbers. So I am going to choose 0. Right? So that would be the square root of 1/5 times 0. And of course, that would just be the square root of 0, which is 0. Right, so there's 1 point. I'm also going to choose, come on, a little bit more line there, there we go. I'm going to choose the point 5. Let's see if you can figure out why I'm choosing these particular points. All right, so we have 1/5 times 5. All right, so 1/5 of 5 is going to give us the square root of 1. And that's just 1. Right? Let's see. I'm going to pick one more point, and that is 25. Right? Yeah, that's actually no. I'm going to pick another. I'm going to pick another point. I have another point I can use. I'm going to choose 20. Then I'll choose 25. Right? Actually, I'm not going to choose 25. Just 20. Sorry, just 20. We have 1/5 times 20. Right? And that's just going to be the square root. Right? So you divide 5 into 20, you get 4. And the square root of 4 is 2. And then I think I'll choose, oh wait, that's it. That's all I'm going to choose. I've got lots of other values on the y, but the problem is they don't fit on my x. So I just kind of got carried away there finding points. So by the way, the next number I would have chosen was 45. Nothing like that's going to fit on that coordinate plane there. All right, so we're going to graph these values here. And actually, the only ones we're going to be able to graph are those two. Because 20 just doesn't fit. All right, so we have 0, 0. And we have 5, 2, 3, 4, 5, 1. Right, and so there's our graph. And we know we're not going to get to 2, right? It's going to take a while for me to get to 2. I'm going to have to go all the way to 20. And my graph here only has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, so I need to go another 7 before I hit 20. All right, and now let's graph the next one. All right, and so we'll plug in for x, and that will give us y, and I'll try not to get carried away here, but I don't think it's really a problem. We found an extra point. I think you're starting, maybe you can see a pattern there. All right, so I'm going to plug in 0. 0 would be a good point for me to choose. So that would be the square root of 3 times 0, which is the square root of 0, which is 0. Right? The next number I could choose 1/3. Right? That would be the square root of 3 times 1/3. 3 times 1/3, that would give me the square root of 1, and that's 1. And I think I'll choose 3. So then I would have the square root of 3 times 3, which would be the square root of 9, which is 3. And am I going to choose any other points? That may be it. Because, well, if I wanted to get 4 as an answer, I'd have to plug in, I mean, we could. We have to plug in 4/3. Right? That would give us 4. Because it would be 3 times 4/3. The 3's would cancel, and I have a square root of 4. If I wanted to get, I mean, excuse me, not 4, 2 as an answer. If I wanted to get 4 as an answer, well, that one's kind of even weirder. It would have to be 16/3. If I wanted to get 5 as an answer, that would be 25/3. So I think 1/3 was good enough. All right, so we'll graph these. I think that'd still be enough. So we have 0, 0. I'm trying to think if there's any other nice points. Not really that are going to fit here. And trying to think if there's anything else. Well, let's see if it comes to me while I'm graphing this. All right, so 0, 0, 1/3, 1, and 3, 3. It would be nice to have another point. Oh, I know. Oh, silly me. This will fit. 12. I'd like to choose 12. 12 is my choice. I have 3 times 12. That's the square root of 36, which is 6. So you can see I'm trying to figure out values that if I plugged in for x would give me perfect squares. If you haven't figured that out, and I did that on both of those because that would be much easier to graph. Even the 1/3 is not bad because it is a terminating decimal. But anything that's not a perfect square is going to be an irrational number. It's going to be a non-terminating decimal, non-repeating. So I was trying to stick with perfect squares. So 12, 6 is the perfect choice. 1, 2, 3, 4, 5, 6. Oops, there's my point. Right, and so here is my graph. And it went just a little high. I don't know if it'll move for me. Probably not. Nope, no, I don't want the clone box. All I asked was that you move. There we go. Was that so hard? Here. That's not where I wanted you to move. Well, I guess it's just going to move right back again, huh? Maybe we'll try to fix that one point. The rest look okay. 1, 2, 3, 4, 5, 6. Just overshot the point a little bit. I'll take it. There we go. All right, so the blue graph was y equals the square root of 1/5 x. And the red graph was y equals the square root of 3x. All right, so let's look at our domain and range. All right, so you can see that there were no numbers less than 0. 0 was the smallest number I chose, and because if I tried to plug in anything smaller than 0, I would get a complex or imaginary number. So 0 is my starting value, and we did go through 0, so we can use a bracket. But notice there's an arrow, so it's going to keep getting larger and larger. We just chose some specific values that were easy to graph. The range, notice that when we take the square root of a number, we only get positive numbers. So the smallest value in our range, we start at 0, and likewise, this is going to keep getting larger and larger. It may take a while for the blue graph, but it will keep getting larger and larger. Let's graph the perfect cubes, and then we're going to talk about the stretch. Let's graph these for the cubes, the cube root of 1/5 x and the cube root of 3x, and then we'll talk about what effect that coefficient in front of x has when it's inside the radical. All right, so we've got, oh, actually, I'll be consistent. We'll graph it in blue. Oop, there we go. All right, so we have x and y, and 0 is a good choice. All right, so we've got the cube root of 1/5 times 0, and that's going to be the cube root of 0, which is 0. Now with the cube roots, I can have positive and negative numbers. All right, so I chose that one. I'm also going to choose -5. So we'd have the cube root of 1/5 times -5, which is going to be the cube root of -1, which is -1. And we'll choose +5. That's going to give us the cube root of 1/5 times 5, which is the cube root of 1, which is 1. Now, remember we said about the cube root, we can't just use those points because it looks like a line. All right, so, but unfortunately, well, I can show you what the value is. What if I wanted to get to the next integer value? All right, so I would have to plug in 40. All right, so the cube root of 1/5 times 40 is going to give me the cube root of 1/5 of 40. 40 divided by 5, of course, is 8, and the cube root of 8 is 2. All right, so even though we try to avoid using just those three numbers, we won't be able to graph these, but at least you get an idea of where the graph is headed. The other one that's also too large to fit would be 1/5 times -40, which would be the cube root of -8, which would be -2. So we can't actually get those points on, but at least we can kind of get an idea of where our graph should head. So we have 0, 0, we have -5, 1, 2, 3, 4, 5, -1, and we have 1, 2, 3, 4, 5, 1. Right, so it doesn't look like a line, but it's not. Right, it's not going to be linear. Right. Come on, point, move where you're supposed to go. All right, and so the next point would be way off the graph. Right, so we know it's not a line. We know it's going to keep going, but we're not going to get there on this particular coordinate plane. Right, we would need more numbers, more space. All right, so there I'm going to try to draw that in. What a slow curve that is. All right, now let's graph the other one. So we have x and we have y. Right, so we'll use 0. So we'll have the cube root of 3 times 0, which is the cube root of 0, which is 0. And we should take 1/3. That would give us the cube root of 3 times 1/3, which is the cube root of 1, which is 1. And we should take -1/3. And gee, wonder what that number could be. 3 times -1/3 equals the cube root of -1, which is -1. And, all right, so let's see if we can get another point on here to actually fit. Perfect cube. How about 9? 9 will work very nicely. So let's take 9 and -9. Cube root of 3 times 9 is the cube root of 27, and that's 3. Cube root of 3 times -9 is the cube root of -27, which is -3. There we go. Now my pen finally caught up. All right, so now let's graph this one. So we have 0, 0, and then we have 1/3, 1, -1/3, 1. I'm a little far on that one, but my dot's so big. And then we need 9 and -9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. And 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. Whoop. And there's our graph. Right, so the only thing is I don't have the parent function on here. So let me throw the parent function on here. He'll be in the middle. So 0, 0, 1, 1, and then 1, 2, 3, 4, 5, 6, 7, 8, 2. Oops, 2. And 1, 2, 3, 4, 5, 6, 7, 8, 2. Right, so there is the parent function. I gotta make sure I aim for the right black point there. All right, so we'll label our graphs. We have the black one, which is y equals the cube root of x. We have the blue one, which is y equals the cube root of 1/5 x. And then we have the red one, which is y equals the cube root of 3x. And before we talk about the type of transformation, let's talk about domain and range. Cube root is all real numbers, so that makes it super easy all the time. If you notice, the black graph is in between the blue graph and the red graph. The blue graph is taking a tremendous amount of time to get to the next y value, right? It's just taking its sweet old time. The red graph, on the other hand, is just zipping to the next y value. So these graphs are has nothing to do with any type of vertical transformation. What's happening here, since we're affecting x, this is a horizontal stretch, right? So it's not a vertical stretch, this is a horizontal stretch, right? So we have a horizontal stretch and a horizontal shrink. The blue one was a horizontal stretch. And you'll have a horizontal stretch. Come on, rest of my word. As soon as, there we go. Any more letters? Most of them. All right. We have a horizontal stretch. And we're going to have a horizontal stretch when the coefficient in front of x, so it's under the radical, and add this to your notes, by the way. When that number is less than 1, we have a horizontal stretch. And what happens is it takes longer to get to the next y value. I really wish my words would come up while I'm writing them. There we go. So I can see if my letters are even readable. The red graph is a horizontal shrink. I think I finished the horizontal, oops, I started to make a T there, shrink. Right, also put this in your notes. And that's when the coefficient in front of x is greater than 1. Actually, let me fix something on this one. Sorry. One little, well, I can easily fix this in. It has to be less than 1 but greater than 0. Right? If it's negative, well, we'll get the same thing. I should put absolute value bars. If it's also negative, then it would be reflected. Right? But if it's a number, positive or negative, between 0 and 1, that's what creates the stretch. Right? Because technically, like -5 is less than 1, and that would actually be a horizontal shrink with a reflection. So when our coefficient in front of x is greater than 1, and it, oops, what happened to the word it? It takes less time to get to the next y value. Right, that would be a horizontal value. That would be a horizontal shrink. Can I get rid of that word value? I don't know what happened there, but that doesn't look so hot. Oh, there goes away the time too. Whoop. That's okay, we'll fix those words. Takes less time, you're probably still writing anyway, to get to the next y value. There we go. All right, horizontal shrink, horizontal stretch, right? So 1/5 here was less than was between 0 and 1, it made our graph grow more slowly. 3 is greater than 1, it made our graph get to the next y value more quickly, right? So it affects your horizontal growth and how fast or slow you get to the next y value, right? So you're stretching and shrinking horizontally. It was the same effect, we won't write it twice, for the square roots over here. Again, the blue graph is taking his sweet old time getting to 2. I had to go all the way to 20. I ran out of graph. On the other hand, the red graph, that's just zipping along. It's already up to 12. And it was on 6 only on the y-axis. Right? So if you have a coefficient in front of x, it's inside the radical, and it's between 0 and 1, your graph grows faster horizontally. Right? Which means it takes longer to get to the next y value. Right? So the growth is horizontal. Right? You're stretched horizontal. Okay? You get really big on the x-axis just to get to the next y value. When it's greater than 1, you are shrunken horizontally. The graph's all compressed. Right? It takes less time horizontally to get to the next y value. Okay? In the next podcast, we'll look at combining our transformations. Thanks for watching. Bye for now.